Hello. Hello.
Hello, Atharv.
Hello. Can you hear me?
Yeah, sir. Yeah,
Okay.
hi. Good.
Perfect.
So, morning for you.
Yeah. Good morning. For
Okay,
me.
nice. Um,
Lot of
what?
confusion over the days.
Yeah, it's not be there. Like from tomorrow, we'll have only MWF. No more postponing or cancellation of the class. We'll try not to do that.
Yeah. Yeah.
Hmm. So you said you had some plan. No, no plans.
No, I don't have any plans now. So what happened is, uh, there was no class on Sunday, right?
Uh-huh.
So I told few people that I will be there.
Okay.
So after that, we decided to have on Sunday. So I just canceled that plan. That's fine.
Okay. So today, as you can see the slide, we'll start with time complexity and basic thing about all these data structure and algorithm, so that
Okay. Yeah. Yeah.
we had those confusions while teaching you what these things mean. So we'll be aware of those things. That we'll start with, and
Yes.
then we'll uh, use this knowledge to talk about few data structure. What is the time complexity of doing various operations in different data structures? And if then if time permits, we'll take some questions.
Okay.
So, did have you appeared for any interview till now? Like, or have you started doing interviews, or you're planning to do it sometime later? What is your status about that?
Yeah, so recently I haven't given any interview, but last
Mhm.
November I gave like few interviews on in Yahoo and Amazon.
Okay.
Yeah,
Okay.
but the issue is my profile is now on semiconductor, right? So
Uh-huh.
even though I am working on software, people think
Uh-huh.
like I am a hardware engineer or I am a semiconductor engineer. So
Okay.
even I got a call for Amazon that was
Uh-huh.
specifically for Alexa and all those devices.
Okay.
It was not specific to the Amazon.com or something.
Got it. Got it.
So they
So,
have the they have that Lab 126 and everything, right?
mhm.
हाँ, so उसके लिए आया था.
Okay. So, फिर, how are you trying to convince HRs now? Do you want to normal interviews for the e-commerce or for the AWS? How do you have it?
Yeah, so I decided कि एक तो सबसे बेस्ट ऑप्शन है कि मैं तो बोल सकता हूँ कि मुझे ज़्यादा यानी इसमें रहना ही नहीं है क्योंकि आई ऑलरेडी हैव एक्सपीरियंस विथ सेमीकंडक्टर एंड आई नीड टू चेंज माय whatever I'm doing. Like this is not
Okay.
the same stuff I wanted to do in my future.
Okay.
So even though मुझे थोड़ा इतना सैलरी वाइज या इतना फर्क नहीं पड़ेगा, बट
Uh-huh.
आई एम रेडी टू चेंज बिकॉज मुझे लाइफ लॉन्ग इसी में नहीं रहना
Yes, got it.
है. Yeah, so
So where did you do your bachelor's from?
from Nagpur, Maharashtra.
Okay, Naku Maharashtra. Okay.
Yeah.
And then master's from?
Um, here there is Sac State, California State University in
Okay.
Sacramento. Yeah.
Okay. Okay. So Vasant is also joining. Let me ping.
आई थिंक उसको मीटिंग मिनट्स मीटिंग की लिंक पता है क्या?
I just gave him.
ओके.
I wasn't.
Yes, I probably.
Yeah. Okay. So only Subhadeep is still remaining. Nice. So let's begin. Everyone is here. Let's start. As I think you can see the slide, data structure and algorithms. The first slide I've shared. You can see, all of you can see that.
Yes.
Okay. Okay. So this class will start with the basic thing again. How to calculate what is time complexity and what is space complexity. What are these things? And then next we'll do some theory. Again, more this class will be mostly theory uh, and less of less of questions, but we'll try to do some questions along with the theory. So as I said, yeah, we'll start with this complexity, the basic thing of the data system algorithm, then stack and queue. Or both the things will complete very fast because they are simple things. They are simple and very simple topic. Then we will talk about few sorting algorithms, so that this is like you have the confidence about sorting whenever you are. There are chances when people end up asking, okay, tell me about this sorting, tell me about that sorting. Although this is very trivial questions, but people end up asking. So you should be aware of at least the common sorting algorithms, what at least the names and what the algorithm is and what the time complexity is. You should be aware of all those things. And then we'll take few questions if time permits. Okay. So yes, let's begin. Uh, so this whole lecture is about data structure and algorithms. So we use different kind of data structures, the data stores, and we apply various algorithms to solve our problem. So we have a problem which we want to solve, and we have an algorithm to solve that, and then using some specific data structure, we get the input. We have to find out that kind of the whole course is about that thing. Okay, so mostly there's a fifth participant. No. Okay. Okay. So most of the solution which we will give, the most of the algorithm which will give to a solution, we'll try to evaluate how good, how bad. But before we do that, first of all, we have to ensure, yeah, that the algorithm which I just gave, the solution which we gave, we have to make sure they're correct. Then only we'll talk about the efficiency and everything. Then only we'll talk about the running time, the time complexity, or the space use, the space complexity. So until we have a perfect running solution, we do not talk about these things every time. Okay. So mostly these complexity, the efficiency which we'll measure will be based on the input size. How big is the input? What are parameters like? So it will be some function of the input size. Most of the time, whenever we tell, okay, what is the running time? What is the space used? So we will take, it will be some function of n. It will be either n square, it will be n log n, or n cube, or e to the power n, 2 to the power n, something like that. It will be, all those will be the function of the input size. So whenever we say it is order of n, we have to specify where n is the size of the array, where n is the length of the array, or where n is the height of the tree, something like that. We have to always, and n is the size of the string. We always have to specify what is this n about. Okay, like this. So nothing bigger till now. All simple things. So I mean, how do we calculate the time complexity? The best case, the best thing would have been just try to calculate using our system only. Try to use our inbuilt methods. We start a timer at the beginning of the program, and then get the timer after the program ends, after the algorithm ends, and then just take the difference. That is what we can do to find the time complexity. But those things are we cannot do in our general life. Those things are very exact time. We don't need that accurate answer. We just need a rough idea. Okay, that is good enough for us to tell the efficiency of algorithm, tell how good or bad algorithm is. We don't have to talk in terms of millisecond now. We just have to take give an idea of running time. How much running time does it? It's like mostly this. It's like CPU cycles. We just have to tell about it. It will take n CPU cycles. It will take n square CPU cycles. We don't worry about millisecond or second. Okay, we don't have to talk about in those senses, in those terms. So for all the classes, we will try to do as much as pseudo code only, because if we try writing running code, that exact running code, we don't have that much time to write running code. And writing a fully running working code, you have to do that when after the classes. Okay, so this is one example of how do we write pseudo code. It's up to you. It's close to English, but near to, and also a little bit similar to our normal life codes. Okay, that's what we'll use to write our solution. This is a first class. Mostly I teach this in a first class, but anyway, so let's go ahead. So there is a sample sorting. Okay, how much this sorting algorithm, how much time does it take? We will start with the example, and we'll try to calculate the time complexity of this solution. So the problem is sort an array of integers. Okay, we have an array of integers 2, 5, 4, 10, 7, and we want to sort it. So what is the time complexity of this algorithm? So you know this earlier only, so you can answer easily. But so for someone who has never done this kind of finding the time complexity, what he will do is he will have to go through the first of all the code, and he will analyze the code to tell the time complexity. So everyone knows what is insertion sort. First of all, like there are multiple kinds of sorting, and what is insertion sort? Does anyone know what is insertion sort? Someone left. Basant, you know what is insertion sort?
Yes, Praveen, I know. What is the insertion sort? In the sense, we are going to consider a key. So based on that key is nothing but assume we have 2, 5, 4, 10. If I consider 2 as a key, and I will compare 2 with the next digits, and I will try to fit the 2 in particular place. Okay, next consider 5. I will go to the 5, and I will consider 5 as the key, and I will try to check out where that 5 should be fit into. It is like consider one element as a key and try to find out its particular place where it can fit into. So that is the sort.
Okay, so great. So you are almost there, and everyone knows what is insertion sort. Let me just repeat the same thing, and I'll try to give you an analogy so that you remember for your whole life what this insertion sort is. The analogy, as you can see in the picture, there is a in your hand there you have lots of cards, and you're trying to arrange that. What you do is you take all the cards on one hand, and your left hand is empty. Suppose your left hand is empty, so you just take card one by one from your right hand, and you try to place it into the left hand in its correct position. You try to insert one card from the right hand where it is not sorted, where it is randomly placed, and you try to place into correct position in your left hand. So initially you have nothing in your left hand, everything on the right hand. So you take one of the card from the right hand and just keep it in the left hand. The next card you take, you insert in again. You try to put it in the correct place, either before the previous card or after the card. But you have to know where the correct position is. Now comes the third card. So the third card, either you have to insert it in the middle or before or after. So this is like what you're doing is inserting into an already sorted part. And how this sorted part was generated? This sorted part only was generated using the same thing only. You try to take one card, kept into the already sorted part. So that is what insertion sort is. So if we also see the same pseudo algorithm, here is a pseudo algo for this, pseudo code for this, not pseudo algo, sorry, pseudo code for this. So what you do is initially your first card is already in the 0th position, or here it is from second as the first position, that we assume it's already sorted. Now we go from 2 to n. This J goes from 2 to n, and for each element it takes, okay, for each it is calling assigning to key. So for each element it takes and tries to insert that value in between 0 to that correct position. Where will that go? So suppose, let's take this example here. 3, 4, 6, 8, 9 is already sorted. Now we pick 7. We have to find what is the correct position of this 7. And actually the correct position of 7 is in between 6 and 8. So we have to insert between these two, and then we also have to shift. Okay, we'll have to shift. We put it here and then shift. Or we can do something else. And then what we want to do is, we want to ensure 0, 1, 2, 3. At third index 7 comes. That's what we have to do. Either we simply insert and then shift, or we do something like, okay, let's paste 7 at 9 position and bring 7 here. Swap 7 and 9, and then swap 7 and 8. And then keep on swapping until you reach its correct position, until 7 reaches its correct position. Okay, that's what we have to do. Ultimately, we have to insert 7 at third index. That's what you have to do. That's why this is called insertion sort. Okay. So we know what is insertion sort. We'll look at all the other sorting, not all, but lots of other sorting algorithm as well. And we'll try to calculate the time complexity of all of them as well. But just talking about insertion sort. So we have this code, which is what it is doing is, for all the element after first element, take that element and try to put it between 0th until that point. Because so when we take 7, we have to insert from 0 to before 7, before this where 7 is. So it runs this external loop for j equal to 2 to n, and in every loop what we do is we try to find the correct position and insert there. So what will be the time complexity now? So at then what we have to calculate is number of cycles it will take, number of CPU cycles. So if you see this line, for j equal to 2 to n, how many times this loop will run? N times, or n minus 2, whatever time. This will run n times. And for every loop, what it does is it tries to insert that a of j in its correct place. This loop will run 0 to n minus 1 times. Okay, 0 to j minus 1 times. For every j, it will run 0 to j minus 1 times. So the time complexity, if you try to calculate very carefully, it will be 0 plus 1 plus 2 plus 3 plus 4, because the first time it will run only for 1 time. This internal loop will run only 1 time, because we know it won't take much time to find the correct place and also shift. But the next case it will run 2 times, and after that it will run 3 times. So total it will be 1 time, 2 times, 3 times, and then total n minus 1 times. So at the end, summation will be n plus 1 by 2. So the total number of loops is n square. So forget about n square. The total number of times it will run is n into n plus 1 by 2. Okay, everyone with me till now? How I calculated n plus 1 by 2?
Yes.
Yes.
Okay. So
For
and then we have
worst
calculated. Yes.
So for worst case, it will be like O of n into n plus 1 by 2. But for
Yes.
base case, it will be like only one loop for that outer for loop. Correct?
Yes. So for the best case, it will be you just pick the number. So it's already sorted. You go to next position. Oh, you already sorted. I don't have to move that number. Again, go back. Go next number. I don't have to move this number. Again, next step. We don't have to move this number. No movement at all. In just every time you just iterate through the external loop and no movement of that number. In that case, it won't be. It will be just 1 plus 1 plus 1 plus 1 n time, which is n time. So Subhadeep, yes, you are correct. Now Now by our convention of or by the rule, but which we follow, and I was going to tell this thing only. Whenever we calculate time complexity, we generally try to talk in terms of worst case, okay? And we don't talk about the best case. We don't even talk about the average case. Actually, from outside, it look like why don't we talk about the average case? Why do you call it worst case? Worst case won't come every time. Why don't? So the thing is, it's not about the exact time which we worry about. It's about the order. It's about the kind of which order it's worrying about. We don't care about if it is 2n or 3n or 4n. We just care about it's of order n. We don't care about it if it is n square, 2n square or 3n square or n square by 2. We just care about itself order n square. That's why worst so most of the times worst and average case are similar only, and that's why we don't talk about the average case also. Forget about best case. Best case is something we don't want to talk about. We chose between average and worst case. What should we talk about? We ended up choosing. We'll talk about the worst case only. We'll always, so because we are comparing algorithms, so we have to take one. So we are taking the worst case of both algorithms, and we can simply compare the worst case. You can also, if you want, you can compare the average case also. In both the case, average case will, if the worst case is for some algorithm better, then the average case also will be better. So that's not a problem. To compare, we can choose either the worst case or the average case. In both the case, the good algorithm is good when you talk about the worst case or average case. The bad algorithm is bad if you talk about average case or the worst case. Okay, so that's what more of this. Okay, this
Sorry to
page.
interrupt.
Yes.
For everyone, this is a slide visible. For me, the fonts are little broken.
For me, visible.
Yeah, I can see.
Oh,
Even I can.
can you zoom the
Zoom.
little more? I think it's okay. Maybe my
Okay.
speed is slow.
Just a minute. This is full screen now.
This is better. This is good.
Okay. Okay.
Thank
So
you.
the same thing we have done here, the calculating the time complexity. So you can see that every time we have written two things: the cost and the number of time that will happen. Okay. So this C1 is the cost. We assume that this loop will running n times, and every time it will take some C1 time, and the next is C2 time is some constant. It will take some 1 second, it will take 2 seconds, something like that. Some constant. This C's are constant, and then we have tried to write one more loop here. This loop will run for the first case, it will run for only one time. The second j equal to 2, it will run for two times. Third j equal to 3, it will run for 3 times. That's what it has tried to write. And at the end, it has included so many variables and all. We don't have to think in this much complex way. We can think in simpler way as well. This is like someone who does not know about time complexity at all, who have never heard about time complexity at all. They will try to calculate even single things and then come up with a total value and then try to find the complexity. But when we are talking about, we'll ignore these constants, we'll ignore this summation formula and all. We don't have to worry about these how to calculate this summation formula and all. We don't have to come up with these kind of representation. Simple, we know we can easily see the two loops. We can count the number of loops in our without even writing these complex mathematics expressions. Okay. Next. So as I told, we mostly talk about we always talk about the worst case and not the best case or the average case. We always talk about the worst case whenever we have to find the time complexity or the space complexity. We haven't talked about the space complexity yet, but whatever we talk about in terms of time, in terms of space, we always talk about the worst case. Okay, so this is a graphical representation of worst case, average case, and best case. We always talk about the worst case, same thing. Again, same thing. So worst case is not much higher than the average case. It's almost similar line, and we worry about only the worst case. So we talked about that insertion sort, and we came to know the time complexity of insertion sort is order of n square. Okay. So apart from that, how much space was needed there in our insertion sort? We did not require any extra space in our insertion sort. we did not require any extra space. It was done in place. We did not require any other space. We just needed 1-2 extra variables. Apart from that, we didn't need any other extra space. So this was in terms of space, it was order of 1 or constant time or no extra space. You can use any term. So order of 1 is similar saying constant time, constant space, or constant, whatever. Yeah, or no extra space. Okay. In terms of time as well, constant time, order 1 time, or no extra time. That you can say that in all these three things means similar. Okay. So in this case, the time complexity is order of n square, where n is the size of the input array, and time space complexity, the amount of space auxiliary space needed, is constant or order of 1. Okay. Done. Simple. So we have seen only one thing. At the end, the crux of finding the time complexity is finding the number of loops. We are not a lot worried about these atomic operations, a equal to a plus aj equal to ai. These are atomic operations, and we are assuming that these things are not taking much time. These things are constant time operations, so we don't have to worry about those things. Most of the times, it is our loop which matters. The loop which we have written, the number of CPU cycles which will be needed to run this program, which has been written by us. Sometimes what happens, it's clearly visible. We can just see the loops, and sometimes it's not clearly visible. We might have to think ourselves. So it takes mostly the case of these cases like recursion. We write a recursion and we think, okay, we have not written any loop, so it will be order of 1. It's not. So sometimes, many times, your loops will not be visible. You have to think yourself, okay, this recursion will be called n times, so the complexity, and in every recursion, it will take order of n, so it will be n square. You have to think yourself. Okay. So but 90% of the time you will be easily able to see the number of loops, and you can calculate also yourself. Okay, not 90, but like 60-70% time it will be clearly visible, and then many times it won't be clearly visible. You have to analyze the algorithm, how many times that code will run. You have to see yourself. So we have done the insertion sort. We'll do another more of sorting algorithms. We'll compare that with insertion sort. But before that, what we'll do is we'll take up 2 data structures today: stacks and heaps. Okay, we'll talk about stacks and heaps and all the operations in stack. No, so not heap. Sorry, queue, stack and queue, and we'll talk about all the operations possible in stack and queue, and the time complexity of all of them, and the space complexity also if needed, and their implementation. So there is a standard question, mostly not a lot of it's not getting asked a lot many times, but thing is this is something you should be aware of. Again, the question like implement data structure A using using data structure B, like, so implement stack using queue, or implement queue using stack, or implement stack using array. This kind of questions also come up sometimes. People end up asking, okay, you know what is queue? Yes. You know what is data stack? Yes. Can you implement your queue using stack? So you should be aware of these things. We'll do some implementation using simple things. So the only data system we have learned or know is array. So the next data system which we will read about is stacks, and we'll try to implement the methods of a stack using an array. But before we implement, we should know what a stack is and what are the inbuilt methods of a stack should be. So we'll learn about that as well. Okay. So again, just before I end, one small thing which is again not needed a lot in interviews, but you should be again aware of these things. Sometimes we have to prove the algorithm which we gave, will it work for all the cases? So there are ways to prove that, but no one asks you. Mostly the things is, okay, they will ask you, do you think this will run for all the cases? Yes, you have to prove, yes, this will run for these cases. You will give example for few cases, and then you will also give edge case example. See, for edge case also it is running. That's good enough. But in college we had to learn this. Okay, few ways to prove your algorithm. So one way we have learned in college, school as well, through induction. So what we do is, if you remember your induction thing, what is proof by induction? Proof by induction is we assume that it will work for 1. We assume it will work for k, and we have to prove that it will work for k plus 1. That kind of proof we used to do, proof by induction. So that is one way to prove. I'm not going deeper. If any of one of you, I'll share the slide. If you can you can go through this. What how do we prove some things, or if you want to understand about induction as well, I'll teach you in separate class, and I'm not spending time here because these things are not asked regularly in interviews. Okay, that prove your algorithm. It's never getting asked. Okay, you have to just give him few test cases. Yeah, see, my algorithm works for this case, my algorithm is for this case, and that's good enough. There is one more way to prove is loop invariants. So what happens in loop invariants is like, you try to prove your algorithm by saying that, see, if my code is already in between, half of it will be already solved. So this means it will be solved for all the other cases as well. Something like that. That kind of proof is also given. Again, not going deeper. We'll do it in, if you want, separately, not now. Okay. Let's move ahead. The important things. I'll move to stack and queues. Any question before that?
No.
I'm unmuting all of you. Anyone has question? Shall I move ahead?
Yes.
Yes.
Okay. Awesome. So the next slide is about stacks. Okay. This is, so before stack, the only data structure we have read till now is array. Okay. And that also we did not try to analyze it very, very carefully, because we have been using arrays since our start of the computer science knowledge, and we know it very well. The only thing we do not know is lots of problem we haven't solved, but we know about how to insert element, how to remove element, and how to find, and we know all those things from very beginning. And we have never seen array as a special data structure. We always thought this is the inbuilt data type, but that's also one of the data structure. Okay, but yeah, so let's go ahead and stack. What is a stack? Everyone knows what is a stack, and if we want to imagine, like, it's something similar to this dispenser kind of thing, or something similar to stack of plates kept in a party. It's like when you keep something, you keep on the top, and when you place that on the top, and every element keep on going deeper, and when you want to fetch, you just fetch from the topmost. So the term it has been given is like first in, what is this, first in,
last out.
last out. Okay, or last in, first out. Last in, first out. LIFO, that kind of word it has been given to this LIFO or something. So this is the property of a stack, something which has been inserted at the last. That if you want to take it out, it takes something out. That is the last which was inserted in the last can be taken out at the first. Okay, that's what the property of a stack is. So the methods which are already there, the standard method which a stack has is push, pop, and top. So push is for inserting, pop is for removing the element, and push top is just to check the topmost element. These three methods are already there in stack. So whenever we use a stack somewhere for our problem, so let me now switch to you can see the screen, the code.
Yes.
Yes.
Okay. So whenever we use some stack in our solution, we just try to initialize, and we assume, okay, stack of type my stack is equal to new stack. This is how we initialize, and then once we have this stack, we can use, we know, okay, we have these methods available now. We can do anything we want. My stack dot push, pop, and top. And then few more methods are also there, which we can use. So our task now is to implement these, how these methods have been implemented or might have been implemented, or how can we implement, given that we want to create our own class stack and we want to write these methods. How can we implement this stack, and how can we make sure like the complexity also not, the method, the running time of these methods are also not are very good. I mean, we can anyways implement in multiple ways. So, which is the best way to implement these methods of a stack? So it's like, what do you do? Whenever I ask a question,
Hmm.
how implement DSA using DSB, data structure A using B. What does this mean? This means you have to write a class A and you have to use B in somewhere. So it's like we can, I'm writing in, yes, something. So
Can you
what does
zoom
this
in?
mean is we have to use B somewhere. So okay, let's initialize some BDS equal to new B, something like this. Okay, so this is what it means. Implement A using B. You have to write a class A and you have to use your B data structure to implement. And at the end, what you do is you have to implement all the methods which are available in a stack. So right now what we're trying to do is we try to implement stack using queue. Okay, so we are trying to implement stack using queue, using array. Sorry, using array. This is what we do. So what we do is implement a class called stack from array. I'm not giving random name. This is a stack I want to implement, and I can use this. Only thing I can use is the array. So S array. Suppose I'm using an S array and initialize with empty array. That's it. And then I have to make sure that all the methods work as it is expected to work. So all the methods like push, pop, push element, okay. So this is what we have to implement. This is what it means. Implement data structure A, which is right now for us stack. Implement stack using array. This is what it means. I have to implement some class called stack with any name, and I can use this array only to implement all these methods. So how will we implement pop? Can anyone tell me how will we implement pop? So before someone tells me, I'll try to use some more variables. So it's like t, okay, some t. I'll make sure we initialize with -1, and let's see. And then we have some capital N equal to some very big number. Some okay. This is the capacity. So this is the maximum size of the array, and this is the index at which the last element is. Okay, something like this. This is the index of the element is. Now using these three things, we can implement our pop, push, and top everything. We can also implement our size method. Then we can also implement our is empty method. All these things can be implemented using these three things only. I have used only one thing, array, and these two variables. Okay, so that's what the question was. Implement stack using array. So I've used array. And now let's implement. So first of all, before I write the code, can people see how will we implement? We have an array and we want to perform push pop top. What will we do? So suppose a new element came. I want to call my stack dot push. So what it should do internally? Where should it push the element? Where should it keep the element? Can someone tell me, Nitesh? What should be the code for push element?
Push, yeah. We can decide to will push element at the end of the array, or at, I think
Okay.
putting at the end will be proper.
Mm-hmm.
Yeah,
Okay.
so we can always put at the end, and we'll pop also from the end.
Okay. So let's see. Let me go back to slide now once. So same thing which I did. Here saying most. So whenever actually I'm doing this for stack, we'll do this for all other data sets as well. We just if so. What is that? Subhadip were trying to write?
I'm trying to write that pop operation.
Okay. Okay. Okay, I have muted everyone. Try not to make some noise from your side, but mute yourself. I am muted now. Okay, so whenever we talk about data structure, we will try to implement. We'll try to insert more, at least these basic methods, which is insert, delete, find. Okay, these are the basic things we'll try to implement. If be it, right now we're doing it for stack, we'll do it for queues also. We'll do it for list also. We'll do it for trees, everything. Some simple binary W-ended queue stack. We'll do it for everything. So right now we're starting with stack, the LIFO, and then we'll see how to implement our push, pop, top, everything. Okay, so as I said, we will try to write a class. Okay, and if you see this class, we have to implement. This is an interface, by the way. We want to implement this size. We want to implement top. We want to implement. So top is empty. We want to implement push an element. We want to implement pop. These 5 things we want to implement. Okay. So to implement these things, first of all, how are we implementing? We are implementing using an array. So that's what again. So in Java code here, we have to implement an array stack. We're naming it array stack using our array. So this is the array we are trying to use S. Okay. So in initializer, if you see, we try to just tell let's initialize our array of size capital N. That's it. Okay, we have just tried to initialize an array and nothing else. Now, once we have our array, and we have few more variables, t equal to -1. What is this t is used for? This t is to just capture where the top element of the stack. This is just to capture that. So if you're using array, it's like index of the last element which was inserted. That's what we are maintaining in this t. So capital S is the array and t is the index of the last element. Using these 2 things and the capital N, which is the size of the array, we'll try to implement everything. So it's the simplest thing, size. What is the size of the stack? How will we return that? So initially the t equal to -1 when there is no element, in the stack, or which means in the array, the t is -1. So the size of the array or size of the stack is 0, t plus 1. So suppose we insert one element. The moment we insert one element, the moment we push one element, will increment t as well. So that's why wherever the last index is, that is t, and if you want to find the size, it's simply return t plus 1, as simple as that. Now, so similarly, the implementation of is empty. So we're just returning if t is less than 0, which means that no element is there. If t is -1, then it is empty. Now coming the most important part, I'll try to write it here. Okay, so just return t plus 1 will give you the size, and return t is less than 0. If it is less than 0, yes, it is empty. If it is more than 0 or more than equal to 0, then it means not empty. There is at least some element. Okay, this is what implementation of is empty and size is. Now we have to insert one element. I'm trying to write that code for one element. Is it correct or not? S of t is equal to new element. That's it. I just inserted the new element at the last. That's it. S of t equal to element. Is this correct or wrong?
We need to increment and then we need to increment it.
Okay, so first, yes. So first, before inserting, you have to increment. You have to increment to the next position. T is the index of the last element. So first, it will be t plus plus and then st of element equal to element. St equal to element. Okay. Correct.
So T is the top, right?
T is the index of the last element. You can say that T is the index of the last element. So if the last element is present at 0th index, we have to insert the new element at the first index. If the last element is at 4th index, we have to insert the new element at the 5th index. So T is so if we first increment and then we first increment T, and then after incrementing, we just place the new element at that position. Okay.
Yes.
Everyone, is this implementation okay?
Yes.
No, but that Stack Overflow we need to check.
Yeah, so we can have extra checks that what if t is more than or equal to n. If t is already equal to n, then we cannot increment t. I mean, we can increment t, but we cannot insert at t plus n plus 1 size. If t is equal to capital N. Now T has already become or
Greater than equal to.
greater than equal to N minus 1.
N minus
N,
1.
yeah. That moment we'll decide, no, we cannot insert anything, just raise some error. Raise error or something. Some exception, okay? Otherwise, you can do simply this. Okay? So that is exception handling, if you can handle that as well. But right now I'm not going into exception handling and all. We just have to implement the simple things. Can we implement this or not? So this will work. Everyone agrees?
Yes.
Now, Subhadeep, you written for pop. Let me just verify everyone. So here written for pop. I think it should be correct. So if t is less than equal to -1, then raise error. There is no element. No, it's empty. Otherwise, first you just decrease t, and you can also, which is correct, t minus just decrease the t, and so that the element at th position is of no use. If you want, you can also do s of t equal to null, so that you don't have anything, and then decrement t. Otherwise, it is not needed also. Even if you just decrement t, that will also be good. Okay, everyone gets this? This is correct.
Mm-hmm.
Okay, nice. We'll move fast since everyone understand this. And what is the top? Top will be just return s of t. Okay. Again, you can handle your exception cases. But okay.
Okay.
Exception will be if t is less than equal to -1. Then if t is less than equal to -1, then just raise stack is empty.
Yeah.
Okay, so we have implemented push, pop, and top. Let's just talk about the time complexity, and then we'll move ahead. So, what is the time complexity of pop?
Constant.
Constant time. Who said?
Atharva.
Okay. Any reasoning, or we can easily see?
Yeah.
We can easily see. There is no loop. We're just doing single operation. That's it. We're doing a single operation, constant time. This is order 1. No. Okay. Great. Others. What about push?
O of 1.
Same. Correct. Order of 1. Similarly for top, order of 1, constant time.
Order of 1.
So yeah. So we have seen the implementation of push, pop, and top of a stack. And if we talk about, like, if anyone asks you what is a stack is, and and if someone asks you, okay, implement stack using data structure something, so you should be know, okay, I know a stack has a method called pop, a stack has a method called push, stack has a method called top, or is empty size. I have to implement these. That's what it means. I have to implement these methods. That's all. Nothing else. I have to create a class. I have to write the empty methods first of all, and then I have to initialize that, use that array or whatever data structure they want me to implement using. So you use that and then implement these methods. That's what it means. And time complexity, we will always try to make it as efficient as possible. Otherwise, the first thing is just implement. Later, we try to check upon the time complexity of these implementations. Okay, we'll do this fast. Okay, we'll do the same thing for Q as well. Let me just go through the slide once before I do the same thing for the Q. We'll take questions, but we'll wait for it. Okay, we'll take questions in the next class, or if possible today as well. So this is same implementation of top and all, which we said, handling the edge cases and handling the exceptional cases and throwing error and all. Okay, same thing which we did for everything. And the time complexity, we'll also try to calculate time complexity. Before that, it has a question. We'll talk about this question later. Algorithm, then nothing special. Yeah. Let's go to the next lecture, queues. Okay, so what is queue? Why I'm taking queues along with stack instead of just doing some question? Because queues are something similar. It's like not similar, but complementary of stack. So most of the places, it will happen that you can use stack to solve it, and then not the queues. But and then some cases you can use queues to solve it and not stack, because the way they work is completely opposite. One is LeFo, the last in and the first out, and this is FIFO, the real life queue. The first who comes in the light has the more pride, has the highest priority. He will come out the first. Okay, that's what LeFo means. last in, sorry, FIFO means first in, first out, and the normal like queues. Okay, so people leave from the front and they join at the rear. We DQ. Okay, leaving from the front means DQ from the front, and we NQ at the rear, at the back. Okay, that's what a queue looks like. A queue in which we DQ from the front. So we have methods like push, pop, and top. We have methods in queue as well, and these methods are NQ. What it means is NQ at the rear. We have DQ. What it means is remove the element from the front. And the last method called front. Just tell me what is the frontmost element. Okay, that's what Q is, and these are the basic methods of Q. We have to implement now. Comes the implementation. We have to implement NQ, DQ, and front. Okay, and this time also we'll use an array only. Okay, now you have to tell me the implementation of Q using array, almost similar as Q. You have to tell me if you all are using laptop, try to just write as soon as possible code for NQ, DQ, and front. And before that, I'll give you some pseudo code so that it's easy for you to implement. Okay, so we are trying to so we want to implement my queue using array. Okay, so I'm writing a little bit in Ruby. You can use Java, C, or whatever you want. So we are using, and again we are using an array, empty array we initialize with, and we have an integer t as well, just to maintain the element. Okay, in this case, just maintaining the t, the element at the last, will not work. We'll have to maintain two indexes in this case, not just one. One, the element, the index of the front element, this is f, and other the index of the rear element. There might be cases when our first index is at fifth position, and the last element is at 10th position. There might be these cases, so we have to maintain both f and r, both of them. Just having one index will not be enough in this case. In stack it was enough, but in array and queue it won't be enough. So we maintain two things. Now using these two things, s, f, and r, I'll show you the slide once. So this is our array which I'm using for our stack. We have element, the first element is at f index, and the last element is at the rear r index. Okay, that is what this is. Now using these f and r and this picture, so you should understand how will we insert, where will we insert, and where will we delete from, and where is the first one. You should be able to answer all these three things using this image, and also I have given you variables s, f, and r. Using these things, you have to implement the size, and then is empty, and then NQ, DQ, front.
So NQ is always to DR, correct?
What?
NQ is always to DR.
NQ is
Always to DR element, DR position.
yeah. Insert the rear element. Yes. So those who have understood, try to implement and try to send the code in the chat. And those who haven't understood, just raise your hand. I will try to make it understand. Okay, looks like everyone is trying, and I will try to go through each one of you code in 2 minutes. Everyone send me your code in the chat, okay? I'll be back in 1 minute. Okay, I'm back now. So I can see a third in NQ code. What you're doing is NQ is S R plus plus is equal to element. Just keep the new element at the R plus plus index.
At the
So
end, yeah.
yeah, at the end. So R plus plus might not be the correct thing. I mean, if R is the index of the last element, then you have to first do plus plus and then R. It won't be R plus plus. It will be
Okay.
plus plus R. Okay. It will
Okay.
pre-addition, not. But
Yeah,
if we maintain the R as the as index of the element, if it is the index of the, I mean, next index, then it's okay. Okay, that's okay.
yeah.
So yes, this is good enough. Now there's one more implementation from a third only. But the front is if it's not empty, then return R, which is return R. No, not return R. Return S of R, not R.
Yeah,
S
yeah,
of
S of R. Yes.
and not R. S of F. Why R? R is the front element, na? Why R? So implementation of this queue, what you're doing is, if you again I should show you the picture. What we're trying to do is, before you implement this, what we're trying to do is, we are trying to remove from front. Okay, so suppose initially there was no element. The first element which came will go at 0th index. The second element, if it comes, it will go at first index. Third element will go at second index. The moment you want to remove, will remove from 0th index. So at that point of time, what will remain with is something at 1 and something at 2, but there will be nothing at 0. Okay, so that's what in mid case, what will happen is, there will be no element from 0 to F minus 1. All the element will start from F and then last element will be at the rth index.
So
So
Praveen, can you
yes,
go on the like first or second slide?
which
Uh,
one?
Maybe before. Yeah, yeah. I think this one. So it
Okay.
says like NQ is insert the object at the rear of the queue, right? So we are actually inserting from rear and even like getting the data from rear only, right?
Getting the data in this, I didn't get.
So basically elements are inserted at the rear. That is
Yes,
NQ.
yes,
So we are inserting the data at the rear and we are also
yes,
removing it from front.
yes.
Okay. Okay. So front is front. Okay. Yeah.
Yes.
F. Yeah.
Okay. So we are removing from front. So there will be a time when there will be nothing at the 0th index, first and the second index, and there will be some. The first value will be at fth index, and the last value will be, last element will be at the rth index. So in this case, in this situation, if we want to implement our coming back to the implementation of front. So what? How will we get the front element? It will be S
F.
of F. That's it.
S of
Return S of F. That's it, na?
yeah.
Okay. Let's talk about a DQ now. I can see the Vasant's code. What he's doing is returning S of F and then F plus plus. Good. So just return F later. Don't return B. First do F plus plus. I mean, first save the. I'll try to
Next
reply.
element.
Yeah, I'll try to write. So Vasant, what you've done is first return and then F plus plus. But if you return, then F won't be plus plus. You won't be able to do plus plus of the return. Okay.
Yes, I got it. To
So,
return.
so we'll store temporary is equal to S of F and then S of F is equal to null also. I'll try to make null also. That's not again needed very much, but
Temp plus plus.
and then F plus plus and then return temp.
Temp. Yeah.
Okay. Cool. So we know you have logged in from now. Is everyone here?
Yes.
I don't know what this meeting came from.
Yes.
Okay, I'll try to close this one. If you want to give me the please assign. Okay. Okay. So we have implemented our NQ, DQ size. Can someone tell me what will the size be?
Praveen, I have pinged you my code on this WhatsApp. I don't have this Zoom in my laptop.
I haven't received anything on WhatsApp, but so can someone just tell me what is the size?
R
So
minus
the front plus R plus F.
R minus F.
R minus F. Correct.
Oh yeah, R minus F.
Okay. Is empty. Subhadeep, what will the is empty be?
F equal to 0 and R equal to 0. Yes.
Yes.
Praveen,
Yes, Nitesh?
I think you would have received in WhatsApp.
You have pinged what?
WhatsApp web in the group.
I'll try to look. Don't worry, I'll try to look. Okay. So here is the code. Here is the code. Just give me a second. Yes. So we can see Nitesh code. All of you. So there's a code for Nitesh also. Size if r equal to -1 and f equal to -1, return -1, else if f is less than r, then return r minus f plus 1. So size is r minus f plus 1, or if f is greater than r. So he has tried to factor other cases as well. I was coming to that, but before I come to that, I will just we'll just write this. Okay, Nitesh, what you have tried to do is we'll talk about that as well. What happens when we have like reached. So what Nitesh has tried to do is he has tried like what will happen if we keep on deleting from front and we reach at the last index. What will happen in that case? Okay, he has tried to factor those cases. We will also do that. Just let me first work with this case. Like suppose we have a very big array. In that case, we will not even reach those cases. Okay, suppose we have a very big array. We'll never be like reaching the end. So that's not a problem. But that won't be the case. There will be a point of time when our f has moved from 0 to n, and then what we do? Then what do we do? Where do we keep our elements? Okay, so those things will also be taken care after we're done with this. So anyway, so someone is saying f equal to 0 and r equal to 0. Is this correct, everyone? Will this be okay? Will this work?
Or we can do R equal to F. That is also works fine. If it is R
That
equal
is
to F.
0.
Yeah, this is correct, but that is not correct. This is like there is no element. This is only the beginning case when we started with our empty array. But moment we started inserting elements, this won't be true. There can be a case where, like we have inserted 5 elements and then we deleted 5 elements. Okay, so we had something at 1, and then we have something at 2, something at index 3, something at index 5, and then we started deleting. We remove the element from index 1, we remove the element from index 2, we remove the element from index 3, and then remove element from 4 and 5. At that point of time, our f and r won't be 0, but they will be same. Okay, so what we have to just check is if this is equal to this means there is no element. This means this is empty. Okay, everyone?
So the size should be r minus f plus 1, right?
Yes, you're talking about edge cases again. I don't care about those things. Depends what your r is, what your f is. Okay, are you calling your front element as f, or are you calling your last element index as r, or the last or the element we can push, that is r? Depends all those things. You can slice them properly and then think properly. Of course, you have to worry about. I'm not worrying about these, but you have to worry about these things when you're writing code. Okay, whether it be r minus f plus 1 or not, you have to of course worry about all those things. Okay, now coming the point which Nitesh was trying to make. What happens when our array is limited size and we end up like, suppose we have elements from 0. Suppose we are currently in a state where we have elements. Let me draw something here. So suppose we started with this. Initially we had something at 1, and then 2 at 3 at 4 at something. We had these many elements. Okay, now we deleted something. We dequeued. So we had null here. We dequeued. Okay, then we have one more dequeue. We have null here. Then we have one more dequeue. And suppose the size was 10 only. Okay, suppose size of the maximum size is 10 only. So we insert one more enqueue. We have 9. We have one more enqueue. We have 10. Now what will happen if you want to enqueue now? Where will you enqueue? Can we enqueue using this, the enqueue method which we haven't written but wanted to write? S of f plus plus equal to element. Will this work here? It won't. It will give array index out of bound exception. Okay. After this point, suppose if n was equal to 10, if n is equal to 10, if you try to insert in this array, it will say, okay, a of 10 is you can't achieve, you can't reach there. This array index out of bound exception will give. So how will we handle this case also now? Your NQ, currently it was working because we assumed that array is very big. But now we are limited size array, we'll have to think about that case as well. The edge case, when we have our last element at the last index, now then one more element is coming. How will we NQ now? What will you do? What will you do? Suppose if f is less than n, then it's okay. Then we can simply insert. But what if f is equal to n? We can't insert at the nth index now. What we'll do? We will try to insert at this side now. We'll try to rotate this. This is something like rotation. We're trying to use the spaces which is available here. Because we dequeued few things, so we can insert here. So we can insert 11 here. Do you understand what I did? Now suppose, so what I'm trying to do is, our rear, which started from 0, 0, 1, 10, it went till 10. Now our rear will become, it can't go beyond 10, so it will become 1. So how will our R grow, or how will our F grow? F will always be equal to F plus 1 whenever we inserting mod of capital N. Similarly, R, whenever we increase R, we'll increase it, but with mod keeping in mind, modulus keeping, modulo, whatever, this thing keeping in mind. Okay, so here wherever we are increasing, so this F we are increasing, F equal to F plus 1. Okay, SFF. Now F is equal to F plus 1, which is what we were doing earlier, but we cannot just do that. We have to do one more thing, modulo of N. Okay, so that we insert and we move ahead. If it is, we have reached the end, we just again rotate back and come to the front. Similarly, wherever we are, okay, sorry, this is NQ is not F. NQ is rare. No one pointed out. This is bad. But okay, so this is what I'm doing. S of R, I implemented R as index, which I can insert, or R plus R index. Suppose R is the place where I want to insert. R is not the index of the last element, but R is the index of the element we can insert, and then increment R. Okay. So do you see what I just changed? A simple change. Instead of just incrementing, simply increment with a modulo keeping in mind, so that you can rotate. Everyone, any confusion? Like I see there's some confusion. I can repeat.
Here my question is that, okay, before inserting, we need to check whether we have null or not in the front row, right? Assume you inserted 11, so we need to check
Yes.
whether F is not in the 0th position.
Yes. So that is also one more check we have to do is, and which is correct. So if so, now let me just clarify once again what our F is and R is, because till now we are just talking. So F is the index of first element, and R is the index where we can insert, or R is the index of last element plus 1, suppose. Okay. One index after that. R is not the index. I'm assuming R is the position, just one after the last element. Okay. Now assuming these two, let's try to write all the code once again. So your NQ will check few things. First, if is full. If it is full, then throw exception. Now we have to implement a throw exception. That here is, we have to implement is full. How will you implement is full?
It should not be greater than n.
No, S plus
The
R
Come
total
again?
size.
is
The
plus
total.
S plus sorry F plus R not greater than N something.
We have size, right? So size is
F plus
should not
R
be greater than the number
is
of element.
size is the, so first let's change the implementation of size only, because now that we are rotating this array, we have to keep those things also in mind. Not every time your r won't be on the right side. This implementation was assuming that we have very big array and r is always on the right side and f is always on the left side. But if you try to rotate, will our r can come before f. So in that case, r minus f plus 1 won't work. We have to handle all these things. So your implementation of size is empty, everything will change. Okay, everything will change. Whatever we did was assuming that we have a very big array and there is no possibility of rotation and all. Now we are saying now we have a very limited size array. So our method of, let's talk about this size. What can be the generic code? First of all, let's write the previous case. If f is greater than r, in that case, sorry, if r is greater than f, if r is greater than f, this means our rare element is at the right side. So in this case, it will be r minus f plus 1. Okay. Otherwise, it will be something else. What will that be?
Yes, RF minus 1 else F minus R.
R plus n minus f. Am I correct?
Yes.
Is this correct, everyone? Subhadeep, do you get this?
Yes.
Okay, even if you do not get this very clearly, try to go through this once again after I end the lecture. This is not very complicated. You can write this on your own. You just have to think about all the cases. What will happen in this case? What will happen in this case? You can just write this simple mathematics. R plus n minus n. Similarly, for is empty, is like if size is equal to 0, is saying, then it is empty. If size is equal to n, then it is full. We can simply use the size method for both things. For is empty also, and for is full also, we can simply use size method. Okay. And then your task is try to write this code which Nitesh also gave, and you also, people will try. First assignment will be try to write these pseudo codes only, not very running code, just pseudo code for just implement your queue using array and handling this rotation case, handling the fixed size array. Okay. First assignment. Now, time complexities. Can someone tell me the time complexity of size? How much time? What is the time of size?
Order of 1.
Is there any other algorithm which is different from order of 1? Any other? Sorry. Is there any other method whose time complexity will be different from order of 1?
No.
All will be order of 1. We don't need any loop anywhere. Okay. Even if you try to do the other implementation of rotated one, that will also, you will check, it will be order of 1 only. Okay. So we have implemented two things. We have implemented two data structures, and both the places we use array only. So in like last half an hour, we implemented two data structure. We implemented all the methods of the data structure, and we also came to know the internal implementation. Okay. Most of the time when we are using these data structure in our problems, we'll consider the methods are available to us. We'll also consider the time complexity of these methods are constant or whatever we have calculated. So we'll consider, and we just have to. No one will ask these implementation again. It's very rare that someone asks you the implementation, and also and it is sometimes they'll use, okay, implement this using this. No one will ask you Can you tell me how is the stack implementation in Java code? Can you tell me how is queue implemented in Java code? There is Java util library. How is that implemented? No one generally asks, but if you're going for a very deep Java question, Java interview, they might ask you. I mean, which is like Java interview. No one ask you in a data structure and algorithm interview. People might ask. There was an interview for me in which they asked me, tell me the implementation of hash in Java, and I think this is a very standard question. So people do ask, but when they care about knowledge of Java and not about the data structure algorithm, they don't ask for you to judge data structure. They ask these questions to judge your knowledge of the language. How good you know your language. Okay. Yeah, that's the assignment for you. And till now, what we have done is time complexity, which was a very simple thing. We just have to find out somehow how many CPU cycles will it take, how many loops it will run. Is there nested loop, or is there like loop one by one? One thing I didn't do is like time complexity. Again, same thing. But we worry about the order and not about the exact time. So few things I'll write is, someone will tell me order of n square plus order of n log n. What will this be? Can someone tell me what will this be?
Order of n.
Order of
N square.
N square. So what I'm trying to explain using this is summation of these two. Suppose you have a solution and you end up finding this. So this will reduce to this only. This will reduce to order n square. Because why? Because we worry about only the worst case, the most slowest part in the algorithm, and not the other part. So if there is multiple part of the algorithm and some part takes order of